Welcome to this explainer, where we're going to unravel one of the most perplexing, frustrating, and, ultimately triumphant chapters in the history of science. It's the story of the rare earth elements.
Okay, let's just dive right in with a question. Think about that smartphone in your pocket, or the brilliant screen you're watching this on right now, or the powerful little magnets inside an electric car. What makes all that stuff possible? Well, if you really want to understand the modern world, we've got to go back in time, way back, to the discovery of the elements that power it.
And this is where the real mystery begins. See, the essential ingredients for our high-tech lives weren't just rare. For centuries, they were completely invisible. They were hiding together in plain sight, masquerading as something else entirely. It's a story that starts, like so many do, with a single weird rock that just didn't belong. So our journey kicks off, not in some fancy, gleaming laboratory, but in the dust and grime of a small mine on a Swedish island, all the way back in the late 18th century. The year is 1787. The Enlightenment is in full swing, and there's this absolute mania for classifying things and for scientific discovery. The Ytterby mine, it had been around since the 1600s, but now it was digging up feldspar, a key ingredient for that fancy porcelain everyone was trying to copy from the East. And right into the scene walks our first character. And here's the thing about the Ytterby mine. It's just so improbable. To an outsider, it's just a pit in the ground, a scar on the landscape. But to a chemist, this place is basically hallowed ground. Through some freakish roll of the geological dice, nature had concentrated a whole secret family of mysterious elements right here, in this one spot. So in 1787, Lieutenant Carl Axel Arrhenius, an army guy by trade but a super passionate amateur rockhound, is checking out the quarry. As he's picking through the rubble, his expert eye catches something odd. It's this black, kind of asphalt-looking rock that was way, way heavier than anything else around it. To the miners, it was just junk, but to Arrhenius, it was a puzzle. He guessed it might be a mineral of tungsten, and naturally, he named it ytterbite after the village. So Arrhenius slips a sample into his pocket and mails little pieces of it off to a few prominent chemists. Now, he had no way of knowing it at the time, but he had just sent out a chemical labyrinth, a puzzle box so complex it would take more than 100 years and the invention of modern physics to truly solve. And that puzzle box? It eventually lands on the desk of Professor Johan Godolin, a meticulous, super precise analyst over in Finland, which back then was part of Sweden.
Okay, now to really get what Godolin did, we need a quick chemistry lesson, 18th century style. See, back then, an earth was kind of the fundamental state of a metal. You can think of it as the great-great-grandparent of what we now call the metallic oxide. It was just a substance that wouldn't dissolve in water, could handle fire, and would form salts with acids. That's an earth.
So Godolin gets to work in 1792. He dissolves the black stone in acid, and then, through all these careful, painstaking steps, he isolates this white substance that behaved like no known earth. It wasn't lime, it wasn't silica, it wasn't alumina, it was something totally new. And 2 years later, he publishes his findings. He announced that a whopping 38% of that original mineral was made of this strange new earth, and he named it yttria in honor of the Ytterby mine. The discovery was a sensation. It really seemed like the puzzle box had been opened, mystery solved. But, and this is a huge but, here's the big twist. Godolin's celebrated discovery was also a profound, though completely unintentional, deception. He believed he had found one new thing. The entire scientific community believed he'd found one new thing. But that black stone from Ytterby, it was holding a much, much deeper secret. So this is the crucial point, right? Godolin was absolutely convinced that yttria was the oxide of a single brand new element. One new earth, one new element, simple, clean, straightforward. But in reality, what he had found was a chemical Trojan horse. This single substance he called yttria was actually a mixture of the oxides of more than 10 different, completely undiscovered elements, all hiding together. And this just brilliantly shows you the central problem. Elements like yttrium, terbium, and erbium are so chemically alike, they're like chemical twins, or triplets, or, well, like a dozen tuplets. They move through simple chemical processes as a single unit, a group that was completely impossible to tell apart with the methods they had in the 18th century. Godolin hadn't found a new element, he'd found a hiding place for a whole crowd of them. And as chemists slowly, painstakingly peeled back the layers of Gadolin's yttria over the next 100 years, they kept naming the new elements after that one tiny Swedish village. It's incredible. Ytterby lent its name, or parts of its name, to 4 separate elements on the periodic table. That's a unique honor in the world of science. Now, while all of this was unfolding, another piece of the puzzle was starting to emerge. Around 1803, another heavy, strange stone was discovered, but this time from a different Swedish mine in a place called Bassnäs. So you have 2 separate teams, one led by the great chemist Jöns Jakob Berzelius in Sweden, and another by Martin Heinrich Klaproth in Germany, analyzing this new stone. And they both independently find another new Earth. Berzelius names it Syria, after the recently discovered asteroid Ceres. And just like that, this established the 2 poles of the rare earth world, the heavy yttrium group from Ytterby and the light cerium group from Bassnäs. So by 1803, the scientific community thought they'd found 2 new elements. What they had no idea about was that each one was actually a complex mixture. They had basically closed the book on the initial discovery, but the real struggle, the incredibly difficult era of separation, was just getting started. This quote right here, it just nails the problem these early chemists were up against. Imagine spending years, literally years, purifying what you think is a single brand new element. You finally get it pure, you're ready to announce it to the world, and then you realize it's not the final doll. Hiding right inside is another, almost identical element. It was absolutely maddening. So to unpack this whole mystery, we're going to follow 6 key chapters. We'll start with the initial puzzle box, then see how a new barcode of light changed everything. We'll watch the chaotic gold rush for ghost elements it created, and see how one ridiculously grueling separation finally cracked the case. Then we'll follow these elements from a dusty lab to every lamppost in the world. And finally, see how this whole scientific hunt blew up into a high-stakes global game. Okay, let's set the scene. It's Sweden in the 1830s. The periodic table is still this kind of messy, incomplete thing. And there are these few weird, stubborn substances that have chemists totally stumped. They look pure, they act pure, but one guy has a hunch that they're hiding a secret. And this is our first detective, Carl Gustav Mosander. Now, this guy wasn't just any chemist. He had a personality trait that was absolutely essential for this field, almost superhuman patience. He was working right alongside the legend, Berzelius, and he started looking again at this element called Syria, and he was convinced, yeah, there's something more to this story. So how do you prove it? With this brutal technique. The idea itself is pretty simple, right? Different elements will crystallize out of a solution at slightly different rates. But the reality of it was just agonizing. He would do these steps over and over and over again, thousands of times, slowly teasing the components apart. And guess what? He was right. Hiding inside Syria was a brand new element he named lanthanum, which comes from the Greek for to lie hidden. How perfect is that? Now you have to remember, for decades, this was all blind work. Chemists were literally just mixing and filtering colorless liquids, basically crossing their fingers and hoping for the best. But then, in 1859, a new tool showed up that was about to turn on the lights. This is the spectroscope, and it was a total game changer. The idea is you heat up a sample till it glows, and you pass that light through a prism. And what Bunsen and Kirchhoff figured out is that every single element has its own unique, unchangeable pattern of colored lines, like a celestial barcode. For the very first time, chemists could actually see the elements they were hunting. I mean, the difference was literally night and day. Before, it was all guesswork based on things like atomic weight. After, you could watch your progress in real time. As you kept doing those crystallizations, you could see the spectral lines for one element getting fainter in the liquid, while the lines for another got stronger in the crystals you were filtering out. The hunt was no longer blind. But here's the twist. This powerful new tool didn't just bring clarity, it also kicked off this huge wave of confusion and false alarms. It sent some of the best scientific minds of the day down a rabbit hole, chasing phantom elements. Take Sir William Crookes, a brilliant British chemist, no doubt. But he was so completely mesmerized by the thousands of spectral lines these elements were giving off that he started to question the very idea of an element. He even announced he'd discovered a new one called Victorium. The only problem, it wasn't real. It was just a complex mixture of other rare earths that was tricking his spectroscope. And Crookes was not alone. The late 1800s became a gold rush for these ghost elements. Scientific journals were just flooded with announcements for these things. Victorium, Discipium, Lucium, none of them were real. They were all just complicated mixtures that looked like a new element's barcode. The puzzle box was now haunted. So while some scientists were off chasing ghosts, others were using these new tools with that same old-school methodical persistence that Moseley had. And in 1885, one chemist made a breakthrough that was so big, it literally changed the periodic table forever.
And this brings us to our next detective, the Austrian chemist Karl Oer von Welsbach. This guy was a true master of fractional crystallization. He decided to take a look at a substance called didymium, which means the twin, because it was always found alongside lanthanum. For 40 years, the scientific world had just accepted it was a single element. Welsbach, he wasn't so sure.
After thousands and thousands of crystallizations, Welsbach proved the twin was actually twins. He split it into two totally new elements, praseodymium, the green twin, and neodymium, the new twin. And just like that, poof, an element that had been on the periodic table for 4 decades just ceased to exist. It was gone. But Welsbach's story doesn't end in the lab, not even close. You see, he wasn't just a brilliant scientist, he was also a really smart entrepreneur. And he was about to find a world-changing application for the very same elements he was spending his life trying to separate. So Welsbach got fascinated by incandescence, that glow you get when you heat things up. He started experimenting, soaking little bits of fabric in different solutions and then lighting them on fire. He figured out that a fragile mesh made of 99% thorium oxide created this perfect, durable structure when you heated it over a gas flame. But it wasn't very bright. The secret sauce, the magic ingredient, was cerium oxide. He discovered that adding just 1% of it to that thorium mesh made the whole thing glow with a brilliant, steady white light. This was the Welsbach mantle, and it didn't just light up cities. It single-handedly saved the entire gaslighting industry from being wiped out by Thomas Edison's new electric light bulb. But Welsbach wasn't done. I mean, think about it. He's got mountains of this rare earth waste left over from getting all the thorium he needs. And being the capitalist he was, he started messing with it. He created an alloy he called mischmetal, or mixed metal, and this stuff had a really cool property. It created a shower of sparks when you scratched it. He had just invented the modern lighter flint, creating the first mass-market product ever for the rare earths. And all of a sudden, everything changed. These elements weren't just weird little scientific curiosities anymore. They were vital industrial commodities. And the lonely, patient work of a few chemists had just kicked off a global scramble for resources that would change the world forever. Welsbach's patent starts a global gold rush for thorium. They find massive deposits of it in monazite sands in places like Brazil and India. The German chemical industry moves fast, forming a cartel that gives them almost total control over the global supply. And then comes World War I, and the Allies have this terrifying realization. Their most advanced military tech, their searchlights, their optics, it all depended entirely on their enemy. The story takes an even darker turn in World War II. As Allied intelligence is sweeping across Europe, they make this chilling discovery. The Nazis had been seizing and stockpiling enormous quantities of thorium. Now, since thorium can be used in nuclear reactors, the question was terrifying. Were the Nazis building an atomic bomb? But the truth? Well, the truth turned out to be almost a farce. After they captured and interrogated German chemists, the Allies learned the real plan. The Nazi conglomerate wasn't building a superweapon. No, they were getting ready for the post-war consumer market. They were planning to launch a radioactive toothpaste called Dormad, and they were stockpiling thorium to make gas mantles for a bombed-out Europe. You can't make this stuff up. Today, we're going to crack open one of science's most famous icons, the periodic table. We're going to solve a mystery that almost broke the whole thing, a puzzle wrapped up in a strange group of elements called the rare earths. You know, the writer Primo Levi, who was also a chemist, he just nailed it with this quote. For decades, that's exactly what the rare earth elements were to scientists, a puzzle box, a secret code, but with no key. So what was this code, and why was it such a threat to the very foundations of chemistry? Well, our story really starts with the table in crisis. To get what's going on, we first have to appreciate one of the most beautiful creations in science, and the huge, glaring flaw right in the middle of it. And here it is, the periodic law. This was Dmitri Mendeleev's brilliant, elegant idea. You just arrange the elements by their atomic weight, and And like magic, their properties start repeating in a predictable rhythm. It was so powerful it actually predicted elements that hadn't even been discovered yet. It was an absolute triumph of human intellect. But then there was this mess. The rare earths. Just look at them, all jammed together into group 3. See, chemically, they were almost identical twins. They all bonded with other elements in pretty much the same way. But their weights were all different. So they just stretched out sideways, completely breaking the neat vertical logic of the table. It was, as some people called it, a chemical run-on sentence. They just didn't fit. Anyway, and you can just feel Mendeleev's own frustration right here. He called them a sea of error. Can you imagine? The creator of this beautiful predictive system had this one chaotic, messy exception that threatened to make the whole thing fall apart. Okay, so if the big theory was broken, maybe the answer wasn't in more thinking, but in just more doing. This brings us to the era of what you might call the brute force chemist. Meet Charles James. This guy, working away in a university basement in New Hampshire, became the undisputed world master of separating these impossibly similar elements. He figured out that the only way to get pure samples was through just sheer, mind-numbing, painstaking labor. And when I say labor, I am not kidding. 15,000. That's how many separate crystallization operations he performed for a single experiment just to prove that one element, thulium, was pure. This wasn't just lab work. This was basically an industrial factory, all run by one incredibly patient man. But here's the thing about James. He was a quiet guy who cared more about being right than being first. Back in 1907, he successfully isolated element 71, but he waited to publish just to be absolutely certain. And in that window, a French chemist named Georges Urban announced the discovery, named it lutetium, and got all the glory. James, the unsung hero, had it first, but he just graciously stepped aside. Now, the chemists, they were doing heroic work, but they were still trapped inside that broken system. The real solution, the key to cracking that cryptogram, had to come from somewhere completely different. It came from a physicist. So this is the big question, right? Everyone was stuck. So, what if the problem wasn't the elements? What if the foundation itself, Mendeleev's law, was built on the wrong thing? What if atomic weight wasn't an element's true identity? And the answer came from this absolute genius, a young physicist named Henry Moseley. Using the brand new science of X-rays, he found something incredible. An element's true identity, its fundamental fingerprint, wasn't its weight. It was its atomic number, the number of positive charges or protons in its nucleus. And folks, this changed, well, everything. So here's how he did it. Moseley would blast elements with electrons and then measure the X-rays they shot back out. And when he plotted the frequencies of those X-rays, he got this perfect straight-line staircase. The chaos of the rare earths, it just vanished. In its place was a perfect, simple integer sequence from 57 all the way to 71. There were exactly 15 steps. No more, no less. Just like that, the cryptogram was solved. And what's so cool is that this discovery didn't just fix an old problem. It gave scientists something totally new, a precise, honest-to-God map for finding all the elements that were still missing. Because the staircase had these clean integer steps, you could literally see where the missing stairs were. Moseley's law pointed to these 4 specific gaps in the known universe of elements, numbers 43, 61, 72, and 75. The hunt for new elements went from a vague search in the dark to a targeted mission. And this law was so definitive, so absolute, people called it a divine judgment. In one fell swoop, it just wiped away years of false claims. All those other new elements people thought they'd found, well, there were no empty spots for them on the staircase. They simply weren't real. They were imposters. But so tragically, Moseley never got to see his table filled in. When World War I broke out, he enlisted. He was sent to Gallipoli, and while phoning in an order, he was killed by a sniper. He was only 27 years old. To this day, his death is considered one of the single greatest losses in the history of science. It almost certainly cost Britain a Nobel Prize. And who knows what else the world lost? What other discoveries were in that mind that had already completely changed how we see matter itself? But Moseley's map, his beautiful staircase, it lived on, and it launched one last frantic hunt for the final missing piece of the rare earth puzzle, element 61. So in the 1920s, finding element 61 became like the holy grail of chemistry. And it was a total frenzy. You had American chemists like Hopkins and, yep, our old friend Charles James, both thinking they had it. Hopkins even named it illinium. Then an Italian chemist claimed it and called it fluorantium. The race was definitely on. Which brings us to a pretty obvious question, right? Moseley's map was perfect. The gap was clearly there, right between neodymium and samarium. You had all these brilliant people looking for it, so where was it? And here's the final twist in the story. It wasn't there. It just didn't exist, not in any real amount on Earth. All of them, all these brilliant chemists, were chasing a ghost. They were hunting for something that nature simply hadn't bothered to save. It turns out, element 61, which was finally named promethium, is fundamentally unstable. It has no stable versions of itself. It is, as our sources put it, a child of nuclear fission. It's only born inside the fire of a nuclear reactor. The chemists back in the 20s never stood a chance of finding it in the ground. And that leaves us with a pretty wild thought, doesn't it? The periodic table isn't just a list of things waiting to be found. Sometimes, to complete the map, you have to build the place yourself.
You know, for decades, a whole chunk of the periodic table was basically a giant question mark for chemists. It was an impossible puzzle. They found these elements all clumped together out in nature, acting like perfect copies of each other, and they just absolutely refused to be separated. So today, we're going to dive into this long-standing chemical mystery and the really elegant theory that finally cracked the case.
I mean, how is it even possible for totally different elements to be so alike that they're practically indistinguishable? What was their secret? To get it, we really have to go back to a time when chemists were, well, truly stumped.
For the longest time, this group of elements, the rare earths, was a real nightmare for chemists. And funnily enough, they weren't always rare, but they were an absolute headache to try and isolate.
Just imagine trying to separate two identical twins who not only look the same, but they also act and react in precisely the same way. That's exactly the challenge they were facing. In pretty much every chemical reaction, these elements behaved as one, which made it almost impossible to figure out where one element ended and the next one began.
So while chemists were working away in their labs, doing endless, tedious crystallizations, the real answer didn't come from a test tube. No, it came from a completely new way of understanding the atom itself. The 1920s brought this huge revolution in physics, and that gave everyone a new lens to look at this old problem.
The main person here was a geochemist named Victor Goldschmidt, who's often called the father of modern geochemistry. He, along with others, started looking at the problem from the inside out, really focusing on the electrons. And Goldschmidt gave this super frustrating family of elements a new name that actually pointed right to the solution: the lanthanides.
And that brings us right to the main idea, the big reveal that explains everything. It's a phenomenon with a fantastic name that perfectly describes what's going on at the atomic level: the lanthanide contraction.
So what is it exactly? Well, to put it simply, it's just the fact that as you move across this one specific row of the periodic table, the atoms don't get bigger like you might think. They actually get smaller. They shrink. Okay, so here's how it works. As you go from one lanthanide to the next, that new electron doesn't get added to the outside of the atom. Instead, it gets tucked away deep inside, in an inner shell. Now, these inner shell electrons are just terrible at their job of shielding the outer electrons from the growing positive charge of the nucleus. So with each new element, the nucleus gets a little more powerful, and it pulls that outer cloud of electrons in just a little bit tighter. And the result? The whole atom just steadily shrinks across the series.
And the outcome of all this is a really clear progression. You start with lanthanum, which is the biggest atom in the series, and by the time you get all the way to the end, lutetium is the smallest. This contraction, this shrinking, is the secret to why they all behave so similarly.
Okay, so atoms are shrinking. Big deal, right? Well, it turns out it's a huge deal. This atomic level detail actually creates the perfect disguise for them out in nature. This shrinking effect has massive geological consequences, and it's the very reason these elements are always found all mixed up together in the same mineral. Here's the most important part. The lanthanide contraction means all of these elements end up with two critical things in common. One, they all form ions with the exact same +3 charge. And two, because of the contraction, their sizes are incredibly similar. This combination is basically their atomic superpower.
There's this fantastic quote from that era of discovery that just says it perfectly. To a growing mineral crystal, these atoms are completely interchangeable.
They've got the same charge, and they're just the right size to pop into the same exact slot in the crystal structure. Nature literally can't tell them apart. You can think of it as the ultimate atomic camouflage. It's why they were always found all jumbled together in minerals, like that famous black stone from Ytterby, Sweden, where a whole bunch of them were first discovered.
But now for the most elegant, most beautiful part of this entire story. The very same phenomenon that created this massive problem of them being inseparable, well, it also held the secret to solving it.
So just to recap, the problem was that they're always found together in nature because they all have the same charge and almost the same size. For most chemical purposes, this makes them pretty much identical.
But here's the key. Did you notice that word, almost? See, while their sizes are very similar, they are not exactly the same. That subtle, progressive shrinking across the whole series, the lanthanide contraction itself, creates a tiny, almost unnoticeable difference in their properties, like how well they dissolve.
And that tiny variance, that was everything. It was the little lever the chemists could finally use to their advantage. By repeating a process like crystallization thousands upon thousands of times, they could slowly, painstakingly, enrich one end of their solution with the slightly larger atoms and the other end with the slightly smaller ones. It was an incredible amount of work, but it worked. The problem contained its own solution.
You know, when you think about the race to build the atomic bomb, you think about physics, right? Oppenheimer, Einstein, massive equations. But what if I told you that in the middle of all that, they accidentally solved a completely different puzzle, a 40-year-old chemistry mystery, and found a literal ghost that had been hiding in the periodic table for decades? It's a wild story. Let's get into it.
So yeah, that's the big question we're tackling. How on earth did the atomic bomb end up solving a chemistry mystery that had stumped scientists for almost half a century? It's really a story of two totally different worlds colliding. You've got the insane, high-stakes physics of the Manhattan Project on one hand, and on the other, this slow, patient hunt for a missing piece of the periodic table. And one, pretty much by accident, is going to solve the other.
All right, first things first. Before you can even dream of building a bomb or a reactor, you have a huge, very practical problem. It's not about the physics, not at first. It's about the stuff you're building it with. The very first giant hurdle for the Manhattan Project was a chemistry problem. They needed uranium, sure, but the uranium they had, it was junk. They needed it to be, well, perfect.
So let's picture it. It's 1942. The world is at war. The Manhattan Project kicks off with this single, terrifying goal: build an atomic bomb before the Nazis do. No pressure, right? And the top minds, guys like Enrico Fermi, they knew that to even get a sustained nuclear chain reaction going, the fuel, the uranium, had to be unbelievably pure. Purer than anything anyone had ever made on a massive scale before.
And the uranium they could get their hands on? It was a disaster. It wasn't some nice, shiny metal. It was this dirty powder, just full of impurities. And these little bits of other stuff acted like, well, like sponges for neutrons. They just soak them up and kill the chain reaction before it could even start. Oh, and the best part? The stuff was pyrophoric, meaning it could just burst into flames in the open air. So yeah, completely, totally useless.
So, who do you call to solve this impossible problem? Well, the job fell to a chemist named Frank Spedding out at Iowa State College. And here's the thing, his specialty was in a totally unrelated field, rare earth elements. But because of that, he was absolutely obsessed with purity. Turns out he was the perfect guy for the job, right when they needed him most.
What Spedding and his team came up with was, well, it was as violent as it was brilliant. They essentially created what they called a bomb. They'd mix uranium tetrafluoride with calcium metal, seal it all up in a big steel vessel, and heat it. And whomp! It would set off this incredibly intense, super hot reaction. And when it was all over, what was left inside were these massive, solid ingots of incredibly pure uranium metal. Just amazing.
And get this, they didn't just make a little bit of this stuff. We're talking about a staggering amount. The Ames process churned out over 2 million pounds of pure uranium for the Manhattan Project. This wasn't some little lab experiment anymore. This was full-on industrial production. And that metal is what fueled Chicago Pile 1, the world's first ever nuclear reactor. So, problem solved, right? The end. Well, not quite.
You know how it is in science? You solve one huge problem and it just reveals another, even trickier one hiding right behind it. And that's exactly what happened here. The reactor worked, but its very success created a brand new, insidious threat, a kind of hidden poison that could literally shut the whole thing down.
So, what was this poison? Well, as the uranium atoms split apart, they create all this atomic ash, basically.
fission products. And a lot of that ash was made of rare earth elements. And soon, the physicists made a really alarming discovery. A few of these rare earths, especially ones like gadolinium and samarium, were what they started calling neutron poisons. They just had this immense appetite for neutrons. If they started to build up inside the reactor, they would just gobble up all the neutrons and stop the chain reaction dead in its tracks.
And all of a sudden, this really obscure academic puzzle, separating rare earth elements, something chemists had been tearing their hair out over for decades, it wasn't just academic anymore. It was suddenly a matter of national security. It was about keeping the atomic pile running and, maybe winning the war. The stakes couldn't have been higher. But here's the catch. These neutron poisons were radioactive. They were unstable, decaying, constantly changing. The scientists had to figure out what they were, and fast. But the way they separated rare earths back then, let's just say it was designed for a different century. It was a science that moved at the speed of a glacier.
Just to give you some perspective, the go-to technique at the time was called the James method. It was this painstaking process called fractional crystallization. It could literally take a chemist an entire lifetime of work just to isolate one pure element. A lifetime. The Manhattan Project guys needed to analyze radioactive isotopes that were disappearing in hours or even days. The old way wasn't just slow, it was completely, utterly useless for this.
So the project was basically stuck. They needed a chemical miracle, and fast. And, like it so often happens in the history of science, the solution came from a totally unexpected place. It was a technology that had absolutely nothing to do with bombs or atoms or rare earths.
Believe it or not, the breakthrough technology that would save the whole project came from water softeners. Yeah, the things that stop your pipes from getting crusty. It was a process called ion exchange, and Frank Spedding's team had the brilliant idea that maybe, just maybe, they could adapt it to solve their impossible problem.
The way it worked was actually pretty elegant. You take your solution of mixed up rare earths and pour it into a tall glass tube that's packed with these little resin beads. Then, you rinse the column with something like citric acid. Here's the cool part. Each rare earth element sticks to the resin with a slightly different strength. So as they wash down the column, they start to separate into these distinct bands, kind of like a rainbow. They travel at different speeds, and eventually they just drip out the bottom, one by one, perfectly pure. And how well did it work? The purity they were getting was 99.99%. I mean, come on. This wasn't just a small step forward, this was a complete revolution. They had taken what was basically a black art, this painstaking process, and turned it into a reliable, fast, industrial-scale science. The change was just staggering. There was a saying that summed it up perfectly. What had taken Charles James a lifetime of labor could now be accomplished in a few days. Think about that. A lifetime of work done in a week. They had cracked the code. But the biggest surprise of all was still hiding in their data.
So now they have this incredibly powerful new tool. And they didn't just use it to solve their reactor poison problem. They pointed it at the fission products themselves, that atomic ash from the reactor. And they were about to find something that chemists had been hunting for decades.
See, for about 40 years, there was this annoying gap in the periodic table, right at element number 61. It was a ghost element. People had claimed to find it over and over again. They gave it all sorts of names like elinium and florentium, but every single time, the discovery turned out to be a mistake. It was just this frustrating, elusive mystery. And then, in 1945, at Oak Ridge, Tennessee, 3 chemists, Marinsky, Glindenan, and Coriel, used their brand new ion exchange technique on the waste from the reactor. And as they watched the bands separate and drip out, there it was. A brand new radioactive element dripping out of the column exactly where element 61 was supposed to be. After 40 years of searching, they had finally found the ghost.
Okay, so they found it. That's incredible. But now, what do you call it? How do you possibly name a new element that was literally born from this terrifying, world-changing new power? Well, the perfect suggestion came from Grace Coriel, the wife of one of the discoverers. She suggested the name Promethium. It's named after Prometheus, the titan from Greek mythology who stole fire from the gods and gave it to humankind, and was punished for it. What a perfect, powerful name for an element born from humanity unlocking the fire of the atom itself.
After World War II, things started to change. The secrets from the Manhattan Project, well, they started to leak out. And with them came this whole new era of research. And, most importantly, a brilliant mind who was finally ready to crack the code. And this is the guy right here, Frank Spedding. His work at the Ames Laboratory, out in Iowa of all places, would literally transform it into the global center for rare earth research. He was the one who was going to finally untangle that mess of the Fraternal 15.
You know, his colleagues had this perfect nickname for him, the Lord of the Rings, which is great, right? It was partly this clever little nod to the electron shells of the atoms he was studying, but mostly it was just pure respect. It was them acknowledging his absolute mastery over this family of elements that nobody else could control. So, the big question is, how did he do it? Well, the key was perfecting this technique called ion exchange. And get this, it was a method that had been developed in secret during the Manhattan Project. Then, in 1947, a huge year, Spedding and his team published a whole series of papers. They declassified the process and just shared it with the entire world.
And the impact? It wasn't just big. It was seismic, absolutely immediate and profound. That one publication sent shockwaves through the entire scientific community. The game had just completely, totally changed. And I mean, look at the results. For the very first time ever, a scientist anywhere in the world could just pick up the phone and order a pure bar of, say, dysprosium or erbium. They'd get it from the Ames lab, and they could finally measure its true properties without all that chemical noise from its look-alike siblings. The Fraternal 15, they were finally liberated. Now, this breakthrough wasn't just some victory for the academics, not at all. It unleashed this incredible wave of innovation that took these elements straight from the laboratory and put them right into our living rooms. And what a revolution it was. I mean, on the one hand, you had yttrium and europium. You put them together, and boom, you get the brilliant, essential red color in every color TV screen. That application drove the whole industry for decades. But at the exact same time, you have another one of these elements, gadolinium, which is this neutron poison that soaks up radiation, being used in control rods to safely manage nuclear reactors. So you've got the same family of elements powering our entertainment and our atomic energy. Incredible. But wait, there's more. This new separation method had another incredible consequence. It finally gave scientists the tools they needed to hunt down this ghost. A ghost that had been haunting the periodic table for years. The missing element 61. And there it is, promethium. In that same critical year, 1947, a team of scientists finally isolated it. And you're not going to believe where they found it, in the radioactive waste from nuclear reactors. They had finally actually captured the ghost. And with that discovery, with promethium, a scientific quest that had been going on for nearly a century was finally over. The periodic table, the fundamental map of all matter in the universe, was, at long last, complete. Okay, so this incredible American scientific achievement, right? You combine that with a huge stroke of pure geological luck, and it leads to something completely new. Total strategic dominance over these supercritical materials. And just look at how fast this all went down. 1947, Spedding publishes the method. The technology is out there. Just 2 years later, 1949, bam, a massive deposit of rare earth ore is discovered at Mountain Pass in California. By the 1950s, it's a done deal. The United States had a global monopoly on these materials. I mean, it was the perfect 1-2 punch. You had the Ames Laboratory providing the brains, the intellectual property, the unique tech to actually separate these things. And then you had the Mountain Pass mine providing the brawn, a massive domestic supply of the raw stuff. You put those two together, you get an unbeatable formula for a global monopoly. And that really brings this whole journey full circle, doesn't it? That weird black stone that was first dug up in a quarry in Ytterby, Sweden, it had been completely transformed. It wasn't just some geological curiosity anymore, oh no. It had become the very foundation, the substrate, of the modern atomic age. And its new home was an American desert.
What if I told you that our entire modern world, everything from your phone to the global balance of power, was basically drawn up by the history of a single, forgotten mine out in the Mojave Desert? Well, today we're digging into that exact story. It's an incredible tale of how this one mine's spectacular rise and even more spectacular fall literally shaped the world we live in.
So yeah, that's the big question, right? How on earth did one patch of rock in the middle of nowhere become the absolute heart of global technology for decades, only to just disappear,
creating this massive power vacuum that would reshape geopolitics. It's an amazing story, full of accidental discovery, incredible innovation, and, in the end, catastrophic failure. To really get why this one mine matters so much now, you have to look at what's going on today. Some people are calling it Tech War 2.0, this global scramble for a handful of special minerals called rare earth elements. I mean, they're the secret sauce in literally everything: electric cars, wind turbines, and even the most advanced defense systems. But here's the thing, this story about our high-tech future, it actually starts way back in the past. We gotta go all the way back to the dawn of the atomic age, when people weren't looking for the future of tech, but for the most powerful and most feared element of the time.
Okay, so picture this. It's 1949. The Cold War is kicking into high gear, and the US is on a desperate hunt for its own sources of uranium to build up its nuclear arsenal. This set off a kind of atomic gold rush, and the deserts of the Southwest became the place to be.
So you've got these prospectors out in California's Clark Mountain Range, and suddenly their Geiger counters start going absolutely bananas. They figured they'd hit the mother lode, a huge vein of uranium. But when the geologists took a closer look, they found something they totally didn't expect. The radiation wasn't from uranium, it was from thorium, which was mixed into one of the richest deposits of rare earth minerals anyone had ever seen.
For about a decade, this discovery was just kinda a cool fact for geologists, a curiosity. But all that changed in the mid-1960s thanks to this brand new technology that was completely taking over American homes: color television. And this new invention, it had a huge, glaring problem. The problem was the color red. Early color TVs were just dim. They were muddy. The reds looked more like a washed-out sad orange. And to even try to make the picture look okay, engineers had to turn down the brightness of the other colors, which made the whole screen look dull. The industry was desperate for a fix. And the solution came from that weird rock out in the desert. Scientists figured out that one of the rare earth elements called europium did something incredible. When you hit it with electrons inside a TV tube, it glowed with this perfect, brilliant, and totally stable red light. It was the magic bullet. And this one discovery didn't just make the picture better, it made color TV a technology for the masses.
So suddenly, everybody wanted europium. And just by a total stroke of luck, the Mountain Pass mine had the richest concentration of it in the entire world. Almost overnight, this one mine started supplying giants like RCA and Zenith, and it just completely took over the global market. Get this, for decades it produced a jaw-dropping 70% of the entire world's supply of rare earths.
But, and there's always a but, behind the beautiful, vibrant glow of millions of TV screens was a really, really dark and dirty secret. Getting that tiny little bit of europium out of tons and tons of rock was one of the most toxic industrial processes you can possibly imagine.
And this wasn't some clean, elegant, scientific method. No, this was pure industrial brute force. First, you blast and crush rock that's over 1 billion years old. Then, you use this complex chemical soup, tons of strong acids and solvents, to painstakingly pull each of the 17 rare earth elements away from each other.
Now, the really crucial part is what was left behind. The process created these huge amounts of waste sludge soaked in powerful acids and nasty chemical solvents. But remember that thorium and uranium? Because the ore naturally had those elements, the waste wasn't just chemically toxic, it was also radioactive, a truly hazardous cocktail.
So, what do you do with millions of gallons of radioactive wastewater? Well, the mine solution was to build a 14-mile-long pipeline to pump all that toxic sludge across the pristine desert to these giant evaporation ponds. And that one decision, that pipeline, would turn out to be its fatal flaw.
Because that pipeline started to fail, over and over and over again. Over the years, it ruptured more than 60 different times, spilling an estimated 600,000 gallons of radioactive and toxic waste right into the sands of the Mojave National Preserve.
An environmental disaster of that scale couldn't be ignored forever. By 1998, facing huge fines and lawsuits, the mine had to stop refining because it had no legal way to get rid of its own waste. Just a few years later, in 2002, with global prices for rare earths collapsing because of new competition, the entire mine just shut down. It was over.
So, the undisputed king of the world's most critical minerals wasn't taken down by a business rival. It just drowned in its own toxic mess, leaving this huge power vacuum on the world stage.
The fall of Mountain Pass didn't just close a chapter, it created a massive, once-in-a-generation opportunity. And while the US was busy dealing with the environmental fallout, another nation was very strategically and very quietly planning to take its place.
And this is where it all comes full circle. For decades, the US didn't have to worry about these materials that were so vital for tech and defense. It had them all. When Mountain Pass closed, that advantage just vanished. China, which had its own huge reserves and frankly looser environmental rules, stepped right in. It methodically built a near-total monopoly, which is what created the fragile global supply chains we're all wrestling with today.
Hey, welcome. We're about to pull back the curtain on something amazing. An invention you've probably never heard of, but it's literally the invisible engine powering almost everything in your life. Seriously, let's get into it.
You've got all this incredible power and precision packed into a sleek laptop. Or maybe it's your phone, right? Think about all those super tiny, complex parts that make it vibrate or play sound, and it all just fits in the palm of your hand.
And what about the cars we drive? The whole electric vehicle revolution is happening because of these incredibly powerful and efficient motors. It's completely changing the game for transportation. Or look at green energy. You see those giant wind turbines out there, spinning away, capturing all that power for our homes? So, what do all these things, laptops, phones, EVs, turbines, have in common? Believe it or not, it's a magnet, an invisible, ridiculously powerful magnet. It's this one single innovation, this one material that links all of these amazing technologies together. And how we got it, well, that's an incredible story of crisis, a global race, and some pretty huge consequences. All right, so to really get why this magnet was such a game changer, we need to rewind the clock. Let's go back to the 1970s, because industry was in the middle of a huge crisis. Okay, this table really lays out the problem they were facing. See, back then, the best magnets around were made from something called samarium cobalt. But here's the deal. The materials were super rare and crazy expensive. And that cobalt, most of it was coming from Zaire, which was politically unstable. So when things got shaky there, the supply chain got cut off, and prices just skyrocketed. You just couldn't build a modern economy on that. The goal was clear. They had to find a new magnet, one made from cheap, plentiful stuff like iron. The race was officially on. So, this crisis lit a fire under everyone. It kicked off a massive global race to solve this problem. And what happened next? Well, it's pretty amazing. So, get this. In 1982, the breakthrough finally happens. But it wasn't just in one place. In one of those no way moments in science, two different scientists, Dr. John Krajat over at General Motors in the US and Dr. Masato Sagawa at Sumitomo in Japan, they both discover the exact same solution at the same time, completely independently. Wild, right? And this is what they came up with: neodymium iron boron. We just call it an NdFb magnet for short. Basically, they found that this perfect recipe of elements, with a little boron thrown in to hold it all together, created a magnet that just blew everything else out of the water. It could pack a ridiculous amount of magnetic punch into a super small space. It completely shattered all the old records. And what's really cool is that even though they found the same material, GM and Sumitomo came up with two totally different ways to make it. Over at GM, they used this method called melt spinning to make these magnetic powders that was perfect for things like automotive starter motors. But Sumitomo went a different route. They used sintering to make these really dense, super powerful blocks, which were absolutely ideal for high-end electronics. So, this discovery wasn't just some neat science experiment. No, this was a turning point. It was the thing that basically unlocked the modern world as we know it. So here's the deal. This is why it matters so much. Because this magnet was so strong but so light, you could finally shrink everything down. All of a sudden, you could build the tiny, precise heads needed for computer hard drives. That's what fueled the whole PC boom. It's the reason you have tiny speakers in your headphones and why your phone can vibrate. In cars, it helped make them more fuel efficient. And maybe most importantly, it became the absolute backbone for EV motors and those giant wind turbine generators. And just to give you a sense of scale, get a load of this. A single one of those huge offshore wind turbines can have up to 2 tons of these neodymium magnets inside. 2 tons. That just shows you how essential this one little invention is to our entire green energy future. It's just staggering when you think about it. But the story doesn't have a simple, happy ending. Because even though an American company helped invent this world-changing tech, the US did not hold on to its advantage. What happened next is a masterclass in, well, what some would call a massive strategic blunder. So let's just trace what happened. It starts in 1982. GM co-invents the magnet. A few years later, they spin off a subsidiary in Indiana to make them, called MagnaQuench. Everything's looking good. But then, in 1995, MagnaQuench gets sold, and part of that sale involves Chinese state-owned companies. And over the next few years, the factories, the know-how, the whole shebang, it all got packed up and moved. By the early 2000s, the US literally could not produce the high-end magnet it had helped invent.
And this wasn't just some random business deal that went sideways. Nope, this was one piece of a much, much bigger puzzle. It was part of a very deliberate strategic plan that shifted the entire supply chain for these critical materials, from digging them out of the ground to turning them into high-tech magnets. From the smartphone that's probably in your pocket right now to the electric cars we see everywhere, our modern lives run on these 17 kind of obscure elements called rare earths. But the story of how they get to us, well, it's an incredible tale of strategic genius, brutal economics, and a truly devastating hidden cost. So let's dig in and uncover the real price of our progress. Okay, so to really get this, you first have to understand the sheer scale of one country's control over these absolutely essential materials. 97%. Just let that number sink in. By 2010, that's how much of the entire global market for rare earth oxides China had captured. And I mean everything. The mining, the processing, the metal making, the magnet manufacturing, the whole shebang. And as we're about to see, this was no accident. Not at all. It was the result of a very deliberate, decades-long plan. So that really brings us to the core question here, doesn't it? How on earth did this happen? How did one single country manage to so completely corner the market on the materials that are essential to pretty much everyone else? Well, the answer doesn't start in some corporate boardroom. It starts with a really powerful declaration of intent right from the very top. Check this out. Back in 1992, Deng Xiaoping, the guy who was basically the architect of modern China's economy, made this now famous statement. And wow, talk about foresight. This wasn't just some clever soundbite. It was a game-changing declaration that would fundamentally reshape national policy and really the entire global economy. And right there, that's the key difference in how they were thinking about this. See, while the West was treating rare earths as just another commodity to be bought and sold on the open market, China saw them for what they were, a strategic asset, every bit as crucial as petroleum. That one mental shift, it changed everything. And man, did they execute on this vision. This wasn't a rush job. It was patient, it was precise. It all starts back in '86 with something called the 863 program. That's when state money started pouring into the tech. Then you have Deng's quote in '92 that just crystallizes the whole strategy. Fast forward to '98, and their economic muscle helps shut down major American competitors. And then, bam, by 2010, mission accomplished, near total control of the market. Okay, so that's the high-level vision, but how did they actually pull it off on the ground? Well, they didn't just have a dream. They had a playbook, a step-by-step guide to systematically taking over the entire industry. And this plan was just methodical. Step 1. The state funds the research to develop newer, way more efficient processing techniques. Step 2. They take that shiny new tech and just hand it over to state-owned companies to scale up production like crazy. Step 3. They use tax rebates to subsidize their exports, making them even cheaper. And the final knockout punch? Step 4, flood the global market with products so cheap that literally no one else could possibly compete. I mean, you gotta understand, this was never a fair fight. It was a complete mismatch. In one corner, you've got Western mines, having to deal with real-world capital costs and, strict environmental rules. And in the other corner, you have Chinese state-owned enterprises being fueled by government money, cheap labor, and almost zero environmental enforcement. It was an impossible fight to win. And the result? The strategy was brutally, devastatingly effective. It kicked off this whole era of artificially cheap rare earths that just wiped out pretty much every other producer on the planet. But, and this is a huge but, that low price tag came with a staggering hidden cost. All right, this is where the story gets really dark. Because China's economic victory, it was paid for. And it was paid for with absolutely staggering ecological and human devastation.
And if you want to find the epicenter of that cost, you have to go to a place called the Bayan Obo mine in Inner Mongolia. This place, discovered way back in 1927, is the largest single deposit of rare earths on the entire planet, and it became ground zero for the fallout from this global price war.
So get this. For every single ton of rare earths they pulled out of the ground, they created tons and tons of toxic waste. We're talking a nasty slurry of chemicals like hydrofluoric acid, and even radioactive stuff like thorium. And where did it all go? Well, it was pumped into a massive 10-square-kilometer man-made lake, a toxic lake that, of course, started seeping into the groundwater and poisoning the local farmland. People who've actually been there, journalists, researchers, they describe a scene that sounds like something out of a sci-fi horror movie. A literal dystopian landscape, they called it, where the shore of this toxic lake is coated in a black crust, and the air is just thick with the smell of sulfur. And the local people, the ones living right there, they paid the highest price of all. These places became known as cancer villages. Residents started suffering from arsenic poisoning, horrifying skeletal diseases, and just skyrocketing rates of leukemia and other cancers, all while their crops were failing and their water was becoming pure poison. Now, I know what you might be thinking. This sounds like a horrible but distant tragedy, right? Well, it's not. It's directly connected to the technology we all use every single day. See, for decades, this environmental nightmare was basically a hidden subsidy for the entire global tech boom. The price of these materials looked low because the real cost, the cost of safely getting rid of toxic waste, the cost to people's health, it wasn't on the books, it was externalized. Basically, it was pushed onto the people and the environment of Inner Mongolia to deal with. And that is the direct link. The cheap magnets in our computers, the little components that make our smartphones buzz and light up, their affordability was paid for by this ecological and human catastrophe. There's really no other way to put it. Today, we're diving into a story that, honestly, it sounds like it's straight out of a geopolitical thriller, but it is 100% real. It's the story of how a tiny fishing boat in the middle of the ocean managed to expose the incredible fragility of our entire high-tech world and set off a massive international panic. So, let's get right into it. Okay, so to really understand the panic that followed, you have to see what the world looked like back in 2010. And this chart, well, it says it all. When we talk about rare earth elements, and you need these for literally everything from your iPhone to sophisticated missile systems, China wasn't just the biggest player on the field. At 97% of all global production, China was the field. This wasn't just dominance, it was a monopoly, plain and simple. All right, so keep that 97% number burned into your brain, because now we're heading out to the East China Sea, where one seemingly small incident is about to light a fuse with some seriously huge global consequences. So here's what went down. September 7th, 2010. A Chinese fishing boat bumps into not one, but two Japanese patrol boats. Now, the key detail here is where this happened. It was near the Senkaku Islands, which are a major point of contention. China calls them the Diaoyu Islands and claims them as their own. So when Japan detained the Chinese captain, this thing blew up. It went from a simple maritime accident to a full-blown diplomatic firestorm, like overnight. And this, right here, is where the whole story pivots. Because China's response went way beyond angry phone calls and diplomatic protests. They decided to pull a very, very powerful economic lever. Almost instantly, Japanese companies, who, by the way, were the world's biggest buyers of rare earths for all their amazing electronics and cars, started reporting that their shipments from China just stopped. Cold. The supply tap was just twisted shut. That's it. But here's the really fascinating part. What was the official story from Beijing? They denied everything. Flat out said, nope, not us, there's no government embargo. They blamed it on things like customs inspections or said it was just individual companies making their own choices. This gave them this perfect layer of plausible deniability, even while the economic pressure was being applied with absolute precision. And this is a classic example of what's called a de facto ban. Right, officially, there's nothing to see here, no ban on the books, but in the real world, for the Japanese companies that needed these materials, the effect was exactly the same. The pipeline was cut. Well, this move didn't just rattle Japan. It sent a massive shockwave across the entire globe. Everybody, all at once, realized that a single country held the keys to pretty much the entire high-tech economy, and they weren't afraid to use them. The result?
total, unadulterated panic. And to just pour gasoline on the fire, on top of this unofficial embargo, China also officially announced it was slashing its global export quotas for rare earths by a whopping 40% that year. They cited environmental reasons. But for buyers in the US and Europe, the message was crystal clear. Supply is about to get really, really tight. And this chart just shows you the chaos that followed. It sparked a massive wave of panic buying. Just look at the price of neodymium oxide. That's a super important ingredient for magnets in things like electric cars and hard drives. It skyrockets from about $50 a kilo to over 300. That is a 6-fold increase. Just insane. And if you think that's wild, get a load of dysprosium oxide. It's critical for magnets that have to work in really hot environments, like in wind turbines. Its price just went vertical, from around $300 a kilogram to a peak of nearly $2,400. It was a massive speculative bubble, fueled entirely by geopolitical fear. So, faced with these eye-watering prices and the very real threat of economic coercion, the world's biggest economies decided they had to do something. They decided to fight back. Not with their own sanctions, but with international law. So in 2012, the US, the EU, and Japan all banded together and filed a formal complaint against China at the World Trade Organization, the WTO. And look, this was not a quick fight. It took years. But in 2014, the WTO ruled against China. And by 2015, after an appeal failed, China had no choice but to officially get rid of its whole export quota system. And the whole legal battle really just boiled down to two different stories. On one side, you had the US, EU, and Japan saying, look, this is obvious protectionism. China is jacking up prices for the rest of the world while keeping them cheap for its own factories. But China's defense was, whoa, hold on. This is all about conservation. We're just trying to protect our environment and these finite resources, which is actually an argument you're allowed to make under WTO rules.
But the WTO panel found a fatal flaw in China's argument, and it all came down to this idea of being even-handed. See, they said if this was really, truly about conservation, then China would have to cut back on how much its own domestic companies were using too. But they didn't. They only restricted what they sold to the rest of the world. And that, in the eyes of the WTO, was the smoking gun, that this was about getting a market advantage, not about protecting the planet.
So, mission accomplished, right? The West won. The quotas were gone, a clear victory for free and open trade. But the story does not end there. In fact, this is where the whole crisis takes this one final, deeply ironic twist. Let's just break down the chain reaction that happened next. Step 1, the WTO rules against China. Step 2, China gets rid of the quotas. And step 3, with all those supply restrictions suddenly gone, global prices for rare earths didn't just fall, they absolutely crashed. And that price crash, well, it had a catastrophic effect on all the efforts to diversify the supply chain.
And this slide really sums up the painful irony of that victory. The bubble popped, prices cratered, and suddenly all those brand new mines that were starting up in places like the US and Australia, they couldn't compete. It was just too expensive. Most of them stalled out or went completely bankrupt. So the great global push to diversify, the whole reason for the panic in the first place, it just fizzled out. The world won the legal fight, but somehow ended up right back where it started, just as vulnerable as ever.
Okay, let's dive into the intense, high-stakes global race for materials that, believe it or not, you're using this very second. This is all about the battle for the essential elements that literally power our entire modern world. For the longest time, the world was, pretty comfortable relying on just one main source for all these critical materials. But that all changed in 2010. A massive geopolitical shock sent absolute panic through global supply chains and government offices around the world. It was a wake-up call you just couldn't ignore. See, before 2010, China had very strategically built up a near-total monopoly. And it wasn't just on the mining, but, and this is the crucial part, on the incredibly complex processing of these elements. This left just about every high-tech economy on Earth in a really vulnerable spot, a fact that became painfully obvious during that 2010 crisis. The first major power to react, and with incredible speed, was Japan. I mean, they were facing a direct threat to their huge electronics and car industries. So Japan didn't wait around for the free market to maybe, hopefully, solve the problem. No, they engineered a solution, and it was completely state-led. And they put some serious money where their mouth was.
We're talking about Japan's Ministry of Economy, Trade and Industry securing a budget of 100 billion yen. That's about 1.2 billion US dollars. And it was all aimed at one single goal: build a brand new, non-Chinese supply chain and do it fast.
Japan's playbook here was just fascinating. The government, acting through its state-owned company JOGMEC, essentially decided it wasn't going to wait for the markets to figure it out. It acted like a venture capitalist with a national security mandate. It bypassed all the uncertainty and directly financed a promising alternative, an Australian mining company called Lynas Corporation.
So here's how it all went down. In 2011, Japanese state and corporate money, a cool $250 million, flowed into Lynas. That cash was used to build a huge, state-of-the-art processing plant in Malaysia, one specifically designed to handle the ore from Australia. By 2013, it was up and running. And just like that, for the first time in years, the world had a major producer of rare earths completely outside of China. The monopoly was officially broken. But it's never that simple, is it? This perfect solution had a major catch. The processing creates low-level radioactive waste. And that, understandably, sparked years of intense local protests in Malaysia. It created this massive political headache and regulatory fights that at times threatened the whole operation. So it became this huge geopolitical asset for the West, but a really controversial flashpoint on the ground. Okay, so that was Japan's carefully executed plan. Meanwhile, back in the United States, a completely different drama was unfolding. The US was also trying to get back in the game, but with a fundamentally different strategy. A strategy that, ended in a pretty spectacular failure.
And you really can't overstate how different these two approaches were. I mean, look at this. Japan's investment in Lynas was coordinated, financed by the state, with a clear, long-term geopolitical goal. The American hope, a company called Molycorp, was the exact opposite. It was totally market-driven, loaded up with tons of private debt, and completely exposed to the wild swings of the market. Molycorp tried to revive its old mine in Mountain Pass, California, with this ambitious plan they called Project Phoenix. But it was a perfect storm. As rare earth prices crashed from their 2010 highs, the company also ran into huge technical problems, and that mountain of debt just became impossible to handle. By 2015, the great American hope was bankrupt.
And just like that, Molycorp became the poster child, the single biggest victim of that boom and bust cycle that followed the 2010 supply shock. The market-driven gamble, it had completely failed. But that is not where the story of the Mountain Pass mine ends, not by a long shot. A few years later, that same mine got a second chance. It was bought by new owners, a new company called MP Materials, and they had clearly learned some very hard lessons from Molycorp's collapse. Yeah, MP Materials took a much smarter and more pragmatic approach. Instead of trying to do everything at once, they started simple. First, just mine the raw ore and ship it to China for the hard processing part. This was brilliant because it generated steady cash flow. They then used that cash to slowly, carefully bring their own processing facilities in the US back to life. It was a classic crawl, walk, run strategy. And guess what? It worked. By 2023, MP Materials was producing separated rare earth oxides right there on US soil. This was huge. It marked the return of industrial-scale rare earth refining to America for the first time in years. A massive milestone. So let's fast forward to today. After more than a decade of state bailouts, market collapses, and slow, pragmatic rebuilding, the global map for these critical materials looks completely different. The absolute monopoly is gone. So here's the scorecard for the world outside of China. You've got two major players on the field now. You've got Lynas, which mines in Australia and processes in Malaysia, all backed by the Japanese state. And then you have MP Materials, mining and now processing in the USA, originally backed by hedge funds and now a public company. Two totally different business models, both managing to carve out a space for themselves. But, and this is a really important but, let's put this all in perspective. While that monopoly is technically broken, China is still the 800-pound gorilla in the room. Lynas and MP Materials are absolutely vital. They're significant new players, but they're still just chipping away at a giant. So the world has options now, which is great, but the supply chain is still very far from being truly diverse. And this number right here is what sets the stage for everything we're about to talk about, 92%. Get this, that is China's overwhelming share of the global market for high-performance magnets. That's the very component at the heart of this whole conflict. To really understand the tech war that's heating up right now, we first have to wrap our heads around the sheer scale of the West's dependency on China. You see, this is a situation that didn't happen overnight, and it's created a massive, massive strategic vulnerability. Now, this chart tells a really fascinating story in 3 parts. You see, China's control over just mining the raw ore, well, that's significant, sure, but its real chokehold, where the real power is in the much more complex and much more valuable later stages. We're talking about the incredibly difficult process of separating these elements, and then the final high-tech manufacturing of the magnets themselves. That's where the power and, frankly, the profit truly lies. And this just brilliantly illustrates the absurdity of the whole situation. It's been called the magnet gap. For years, the US has literally been digging raw materials out of the ground in places like California, shipping all of that ore across the ocean to China to be processed, only for American companies, think car manufacturers, to have to buy the finished high-tech magnets back from Chinese suppliers. I mean, it's a broken supply chain by design. But it gets even more specific than that. Not all rare earths are created equal. The most critical vulnerability actually lies with the specific subset called heavy rare earths. We're talking about elements like dysprosium and terbium. So why do they matter so much? Because these are the essential ingredients that allow magnets to keep their power in the high-heat, high-stress environments you find inside an electric vehicle motor or a giant wind turbine. Without them, the green revolution pretty much stalls out. And hey, if you thought 92% was high, look at this, 99%. That is China's control over the refining capacity for those vital heavy rare earths. It is a near absolute monopoly on the secret sauce for our most advanced green and defense technologies. And this, right here, is the core of the West's strategic problem. So you have to be asking, how on earth did this happen, right? How did the United States, which once completely dominated this entire industry, find itself in such a precarious spot? This timeline really tells the whole story. If you go back to the 1980s, the US was the undisputed leader across the entire supply chain. But then, a series of decisions mostly driven by short-term thinking and just a failure to see how strategic this industry was, changed everything. The real turning point was in 1996, when a crucial US magnet tech company called Magnequench was sold to Chinese interests. Now, fast forward to today, and the West is basically trying to rebuild an entire high-tech industry from scratch. But the story doesn't end there, not by a long shot. After recognizing the danger, Western governments and companies are now mounting this massive, coordinated response. The race is officially on to create a parallel supply chain, one that's free from this dependency. And this is basically a 2-pronged government assault on the problem. Over in the US, you've got the Inflation Reduction Act, which uses these powerful tax credits to push car makers to use minerals and parts from the US or its allies. It also explicitly excludes components from what it calls foreign entities of concern, which is a pretty clear shot at China. At the same time, the EU's Critical Raw Materials Act is setting these really ambitious targets to bring mining and processing back home by 2030, all to secure their own supply chains. And we're already seeing this strategy play out in the real world. A company called MP Materials is executing this plan to finally close that magnet gap we talked about. So they're mining in California, but instead of shipping to China, they're now processing the material at a brand new facility in Texas, with the final goal of making the finished magnets right there. They've even locked in a huge supply agreement with General Motors, which proves that a fully American supply chain is actually possible. But like I said, this is a chess game, and China is not a passive player. Just as the West starts to rebuild its own capabilities, Beijing has made its own powerful countermoves, all designed to protect its dominance. And this was a masterstroke. One source called it a surgical strike. In late 2023, China banned the export of the technology itself, the actual know-how for processing these elements. It's like hiding the recipe after your competitors have finally found all the ingredients. This one move dramatically increases the cost, the time, and the complexity for any new Western projects. And they didn't stop there. Beijing followed that up by requiring new export licenses for the raw materials themselves, all under the banner of national security. What this does is add a powerful layer of uncertainty. It basically gives China a faucet, the ability to turn the tap on and off, throttling the supply to specific countries or even specific companies whenever it wants to.
All this pressure has sent the West scrambling for alternatives. And one country has really emerged as the great hope for diversifying the supply chain away from China: Vietnam.
Now, on paper, Vietnam looks like the perfect solution. I mean, it has the world's second largest estimated reserves. But the reality on the ground is way more complicated. The development of its industry has been completely paralyzed by corruption, technical setbacks, and even recent arrests of top mining executives. So for now, Vietnam remains a sleeping giant. It's not yet a viable large-scale alternative that can solve the West problem.
So as the green energy transition speeds up and our world becomes even more reliant on these technologies, we're left with this really fundamental question. The revolution is absolutely happening, but the contest for control over the very elements that make it all possible, well, that is just getting started.